So in simple harmonic motion, there are two main equations that you'll learn. Both of them are used to calculate the period. And there's different elements to these equations, and I'm going to break down how to derive both of them bit by bit. To derive the spring period function, we need to first realize that it comes from centripetal acceleration, and we'll list out all the equations after you look at this one simulation. Okay, so this is how we can derive it. Originally, this is our centripetal acceleration equation. We have velocity squared divided by r. Now, we have centripetal acceleration again, but we could just condense velocity squared divided by r into omega squared times r. Now, we have a centripetal acceleration equation. We equaled that to omega squared times r already earlier. But we can substitute omega in for 2 pi divided by period. And by substituting that into omega squared, we get 4 pi squared divided by period squared. We also substitute r in for x. Okay, so earlier I said that r is equal to x, and I didn't really specify that. And here's why r might be equal to x in this case. So if you look back to our original simulation, we have our circle thingy, and this is our center mass, and then this is the radius on how it is. So this is r, and when we flip it into the two-dimensional thing, it looks more like a spring. And let me actually draw it as a spring just to make more sense. So let's say this is our cylinder on the two-dimensional side, and as you can see, there's like a mass that's going from here to here, and this change in position is basically change in x. So r and x are equivalent to each other. And let me draw another picture just to make more sense.
So let's say that this our spring thingy, right, is the spring, and this, let's say that's the plane that it was on, and this is the circle. So if we saw the difference,
right, if the circle just accelerates to the side, it's just going around in a more circular way, just as this. It's just going to the side and back. Same thing. You can see the parallels between them. So our original radius is now x, and we'll explore why that is in a second. So we have, this is our new equation for centripetal acceleration, and that already is starting to look like the period equation. We just now we substitute the centripetal acceleration into kx divided by m. I just want to take a second to figure out how we actually got this. If we want to say the spring equation for F net equals to kx, right? This is our spring equation regularly. F net equals to kx. F net is also equal to ma, and ma is equal to kx. If we divide m on both sides and isolate a, we get kx equal to m. And the acceleration in this area, we're basically converting that into centripetal acceleration. But that's how we got this original thing, and we just plug it in. That's basically it. And now you have kx divided by m over here, and equal that into whatever we got earlier. Now we can take away x on both sides, which leaves us with this equation. And this equation can be further simplified, and isolating t would give us this final period equation that we see earlier.